Hello. Now, in this video, what I want to look at is some issues that aren't really about the shape of the Earth, but with flat Earth proponents, they become so kind of mixed up with the whole thing that I thought it was worth making a video about it. And what I'm talking about is issues related to the rotation of the Earth and the Earth moving around the Sun and the solar system moving through the galaxy. And I'm quite sure you've heard the peculiar things that they say. They've got this, it's almost like a meme that they've got that they repeat over and over. The Sun, what is it, the Earth's spinning at 1,000 miles an hour and it's moving around the Sun at 67,000 miles an hour and it's moving around the galaxy, blah, blah, blah. Without really giving any argument about what that means or what the implications of it are or why we should be aware of that. Now what I need to do for this one is really just go back and do some really basic physics. And what the first thing I'm going to talk about is something that's in physics is known as, it's variously known as the principle of relativity, the principle of inertia. It's pretty much contained within Newton's first law of motion. And it goes way, way back. It goes right back to Galileo. And it's, you know, you could say it's kind of the start of what we know as physics. So you can see in front of you, and here I've got two coordinate axes drawn with two little people on each one. So each person has got their own coordinate system, an XY coordinate system. So this person is a certain distance x along and y up in their coordinate system. And this person's a certain distance like x and a certain distance y in their coordinate system. Now we'll just stick to two-dimensional. In real space there'd be a third axis, a z-axis, but it doesn't really make much difference. Now supposing if this person, if we consider it from the perspective of this person here, and this person's moving up like this, then in this person, as far as this person's concerned, they're stationary within their coordinate system and this person is moving past them. Now supposing this person is moving with a constant speed in a straight line. So if they're moving with constant speed in a straight line, we say they're moving with constant velocity. Because velocity is speed in a given direction. This person here, though, could claim within their coordinate system that they're stationary and that it's the other guy, the other person that's moving. So they could claim that they're stationary and the other person's moving in a straight line at a constant speed, but in the opposite direction, like this. So the question is, are either of them correct? Is either of them wrong? The answer to that is that they're both correct within their own frame of reference. What we call this is a frame of reference. And if they're moving with a constant speed in a straight line, it's called an inertial frame of reference. And as you might recall from Newton's first law of motion, if something's moving, it will continue to move in a straight line with the same speed unless something happens to change what it's doing. But we'll talk about that in a minute. So there's a symmetry in this situation. But we say that both inertial frames of reference are equivalent, or there's no way of distinguishing between them. Another way of saying that is if, say, both of them did an experiment, a physics experiment, then both of them should get the exact same results in that experiment. If one of them's, even though they're moving relative to each other. Another way of saying this is that there's no definition of absolute zero velocity. There's no definition, there's no way of physically defining a rest frame, a reference frame that's an absolute rest. There's no known way of physically defining that. All frames of reference, as far as we know, are physically equivalent. There's no way of distinguishing between them. Suppose then that this guy is stationary as far as he's concerned, and this guy goes by slowly and then starts to speed up. So he's accelerating like this. Maybe not showing that very clearly, but... Well, just from purely geometric considerations, you could say that this guy, or this person, could claim they're stationary, and it's this person here that's accelerating this way down here. The question is one of them correct and one of them wrong? And the answer is yes, one of them is correct, because this situation lacks symmetry. If this one here has a force acting on him, then he's accelerating, and he's not in an inertial frame of reference. This one is an inertial frame of reference, so he's the one that's, this one's the one that's correct. He or she, sorry, person, he or she is the one that's correct in saying that they are not accelerating. They're in an inertial frame of reference. Within their own coordinate system, they're stationary. This is the one that's accelerating. And Newton's second law of motion tells us that the rate they accelerate at is proportional to the force acting on them, the unbalanced force. There could be more than one force acting on them, but overall there'll be one unbalanced force. I mean, this person could have forces acting on them, but they could all be cancelled out. So there's no unbalanced force, so they're not accelerating. So there isn't a symmetry in that situation. Acceleration is an absolute measurement. It's not relative. It doesn't depend on what frame of reference you're observing it from. As long as you're observing it from an inertial frame of reference, as long as you're not accelerating, it doesn't matter what speed you're travelling at. The acceleration that you observe someone else experiencing is an absolute measurement. It's directly related to the force acting on them, which is a physical measurement. So this has a real physical meaning. I'll just touch on another point here. You could also have one of the reference frames rotating like this. Now, a rotating reference frame is not physically equivalent to a non-rotating reference frame, because geometrically you could say that this is kind of the same as this. Maybe I'm not showing that very clearly, but that was moving around a circle like that. Geometrically, yeah, they are the same, but they're not physically the same things. There is a physical definition of a non-rotating reference frame, and it's to do with forces. Now, what we need to talk about is rotational motion, or circular motion specifically. So, I've got a circle here. So imagine there's a point on this circle here, and it's moving with a constant speed, but around the circle. Now, its speed is constant, but its direction is constantly changing. Therefore, it's accelerating. When something is moving in a circle, it is constantly accelerating towards the centre of that circle. So we've got this circle, we've got something moving in a constant speed around it, and the circle has a radius, say it's radius r, and now the object has a speed or velocity, which is what we call a linear velocity. Now that's something you might measure in miles per hour, meters per second, something like that. But we don't measure how fast something is rotating or moving in a circle with something like that. Now, this is one of the things that I hear so many times, people saying the Earth's spinning at 1,000 miles per hour. That means nothing. It's an empty, meaningless statement. you do not talk about something rotating in miles per hour. Miles per hour is a change in distance divided by a change in time, which is a speed or a velocity if you're combining speed with direction. We measure rotational motion as an angular velocity, a change in angle divided by a distance in time. Sorry, divided by a change in time. So for example, the Earth rotates at 1 rotation per day, so it's turning through 360 degrees in 24 hours, so it's about 15 degrees per hour, which is actually very, very slow. I mean, flat earthers want you to believe that the Earth is rapidly rotating. It's not. It's turning very, very slowly. I mean, to get that in perspective, imagine the hour hand on a clock going round the clock. Well, the hour hand man rotates once every 12 hours. So that's rotating at twice the angular speed of the Earth. So I think you can see the Earth is not rotating very fast. However, we'll come back to that. Now, when something's moving in a circle, when you first learn about this, it seems slightly counterintuitive. It's actually accelerating towards the centre of the circle, no matter where it is. It's moving with a speed that's a tangent to the circle, but it's accelerating towards the centre of the circle. Now, there's a quantity that I want to define that's properly. I mentioned it already, but it's angular velocity or angular speed. Now, the proper way of doing this is not in degrees per time interval, it's in radians. Radians are the proper units, the natural units for measuring an angle. Now we know that a circle is 360 degrees in it. Most people know that, I'm sure. But it's also got 2 pi radians, which is 6.28 radians in a full circle. So angular velocity is defined as 2 pi, that's a full circle, divided by the period. Now the period is the amount of time it takes an object to to go around the circle once. It completes one complete turn of the circle. It goes all the way around. Now obviously that's going to be in units of hours, seconds, whatever. Now I'm going to give you a formula here without justification. You can look this up online. It's on Wikipedia. You can find it in lots of places. If anybody's interested, I can make a video justifying this. It requires a little bit extra mathematics. It requires a little bit of calculus to justify this formula. But it's quite simple. It's basically that this acceleration towards the centre of the circle is given by the angular speed squared times the radius of the circle. And that's a formula we're going to use. So you work out the angular speed, you square it, you multiply by the radius of the circle, and that tells you what this acceleration is, so that when this object's moving in a circle, it's accelerating towards the centre of the circle, wherever it is on its journey around the circle. It's always accelerating directly towards the centre of the circle. And acceleration is given by this. Okay, so let's consider what the acceleration then is when you're on the equator. So suppose this is the Earth and you're looking down on it. So suppose this is the North Pole and you're looking down on it. So this is the equator around here. And there's a point on the equator and it's, so let me think, if we're looking down, the Earth should be spinning anti-clockwise. Does that make sense? Let me think. Yeah, it does. So it's going to be moving like this. Yeah, because as you move around, the sun comes from the east, so that makes sense, doesn't it? Yeah, good. Now, so the radius of the Earth. Now I'm going to do this in meters. Now I'll become clear. I'll explain in a minute why I want to do this in meters. The radius of the Earth in meters is 6,400,000 meters. So it's 6,400,000 meters. Now the period is, now remember the period is how long it takes to do one complete return and one complete rotation. Now it's 24 hours, but we want it in seconds. And again, I'll explain why that is in a second. Now, so there's 60 seconds, 60 minutes, and an hour, and there's 24 hours, and that gives you 8,6. Sorry, not that. That gives you 8,6,400 seconds, 86,400 seconds in a day. And let me check, that's 60 times 60 times 24, 86,400 seconds. So 60 seconds times 60 minutes, and an hour times 24 hours, that gives you 86,400 seconds. So we can now calculate the angular speed of a point moving around the equator, which is going to be 2 pi divided by 86400, which comes out as now that's 7.27 times 10 to the minus 5, so that's 0. I'll just write it in long form. So it's 0.0000727 radians per second. So we're now in a position to calculate what the acceleration is. So remember what I said, wherever this point is, it's accelerating towards the centre of the Earth with acceleration A, we'll call it. So it's moving around and it's always accelerating towards the centre of the Earth. So the acceleration due to the rotation of the Earth is 2 pi over 86400 squared. Remember, it's the angular speed squared times the radius of the Earth, which is 6,400,000, and that gives us, so you've got 2 pi divided by 86400 squared times 6,400, 0.03 meters per second per second. Now I'll write it like that. It can be written as meters per second to the -2, but it just means meters per second per second. Now I deliberately calculated it in those units because it can give you, because it'll help put it into perspective exactly how big an acceleration like that is. If you drop something to the ground, if you're holding an object and you drop it, it'll start accelerating towards the ground with an acceleration of g, which is 9.8 meters per second per second. So I think you can appreciate just how slight this acceleration is due to the rotation of the Earth, due to a point on the equator and the Earth rotating, making it accelerate towards the centre. It's only 0.03 degrees. Sorry, not degrees, 0.03 meters per second per second. Now that's about So let's do 9.8 divided by 0.03, about 1/327th of g. That value there is 1/327th of g. Now the upshot of that is, all it means is that if someone's at the equator, they weigh about 1/327th less than they would at the North Pole. That's the only effect. And it would be very difficult to... I calculated it. I mean, it's like about £1 or something. Difference or something. I can't remember what it is. It's not much, anyway. For someone of a certain weight, it's only maybe about £1 or so, if you're about average weight, I think, or a normal sort of weight. So it's not an awful lot. So it's only 1/327th lighter than you are at the North Pole. Now, we wouldn't even be aware of that acceleration. To give you some kind of indication of that, imagine that this here is a disk, or say like a kind of roundabout with a radius of 3 meters, and you're sitting on the edge of it here, and it's got a period, it's rotating with a period of 60 seconds. So it's kind of going round like this, but it's taking a minute. So it's just a disk with a radius of 3 meters. You're sitting on there, it's taking a minute to go all the way around. So it's just like a kind of roundabout, really. Well, what would the acceleration be? Well, the acceleration would be 2 pi over 60 squared times 3. So I'll just make sure, I'll put this there. The angular speed would be 2 pi over 60, which is what I've got here, squared, times the radius, 3, and that would give you 2 pi divided by 60 squared times 3, 0.03 meters per second per second. So these two situations will give you the same acceleration. Being at a point on the equator and the Earth turning once every 24 hours, and being on the rim of a disk with a radius of 3 meters and turning once a minute, you'll get the same acceleration. Now, as it turns out, the actual linear velocity or linear speed of a point on the equator is about 1,000 miles per hour. But that is a fact that in of itself means nothing. All you're saying is that you're moving at 1,000 miles per hour relative to the Earth. And as I've already talked about, speed is a relative measurement. It doesn't mean anything. And when you know, if you're on a train and it's speeding along 100 miles an hour, it doesn't feel like you're moving. You could juggle on a train and you would have no problem doing it. You'd only feel slight vibration due to the movement of the train. Nothing serious. However, if that train starts to speed up or slow down, you start to feel it. Because that's where forces come in and you're no longer in an inertial frame of reference. You're slowing up, speeding down, you're accelerating. And that's what matters. That's what affects you. It's forces and acceleration that you're aware of, not velocity, because velocity or speed is relative. I mean, you might as well say that this point is moving at a certain speed relative to Mars or relative to the Andromeda galaxy. It doesn't matter. It doesn't mean anything. This 1,000 miles per hour fact really is of no significance at all, other than telling you that that's what speed you're moving at relative to the reference frame of the whole Earth. Now, the other one that they go on about is another couple of circles. I want to run through these fairly quickly. The other one that they'll tell you about is the sun. And they'll say that, so say this is the Earth, and it's moving in a circle around the sun, like this. Now the radius of the sun is 1.5 times 10 to the 11 meters. So that's 1.5 followed by 10 zeros. And the period, how long it takes to go right round the Earth to rotate the sun, is 60 times 60 times 24 times 365, which equals, I'll put it down here, 31536,000 seconds. I'll just double check that calculation. I've got it written down now. Times 60 times 24 times 365, 31536,000 seconds. That's the number of seconds in a year, basically. So the angular velocity of the sun, of the Earth, sorry, as it moves around the sun, is 2 pi over 31536,000. The radius is that, so the acceleration due to the Earth moving around the sun is 2 pi over 31536,000 squared times 1.5 times 10 to the 11, and that's 2 pi divided by 31536,000 squared times 1.5 exp 11, which is about 0.006 meters per second per second. That's the acceleration you experience due to the Earth moving around the sun. Put that in perspective. Again, imagine you're on the disk. It's got a radius of 3 meters. I suppose in the period is 140 seconds. And so that's about 2.3 minutes. Then the acceleration is 2 pi over 140 squared times 3 . 140 squared times 3, which is 0.006 meters per second per second. So the acceleration that the Earth experiences due to its rotation around the sun is 0.006 meters per second, which is the same as the acceleration you'd experience if you were sitting on the edge of a disk and it was rotating once every 2.3 minutes, every 140 seconds. So you're moving very, very slowly around this disk. Now, once again, the Earth is moving with a certain linear speed or linear velocity relative to the sun, which is about 67,000 miles per hour. Again, so what? Really, it doesn't mean anything. I mean, you might as well say how fast it's moving relative to a planet in another galaxy, or, you know, it doesn't really mean anything. Velocity is relative. Again, all that matters is forces and acceleration in determining if things like this are affecting the object or anything that might be affected, or whether people on the Earth would notice this. Now, I've heard people say these figures as if it proves that that can't be true, and it's meaningless what they're saying. It's meaningless. And I've heard people say that that because the Earth is spinning at 1,000 miles an hour, we should fly off it. Well, would you expect to fly off a disk if it was moving a 3-meter disk, if it was turning once a minute? Because that's the same acceleration. It's the same forces you'd experience at the equator. Why would you experience that? Why would you notice it? Why would it cause you to fly off or something insane like that? Right, let's do one more. Now calculate one more for the solar system. Oops. So the solar system's moving around the galaxy, roughly in a circle. Just in case anyone brings it up, I know that the Earth doesn't move in a perfect circle. It moves in a slight ellipse around the Sun, but it's pretty close to a circle. It doesn't affect what I'm saying at all. It doesn't really affect the mathematics that much. So the solar system's circling the galaxy. The galaxy, or well, not the galaxy, but the distance of the Earth to the centre of the galaxy is 2.4 times 10 to the 20 metres. So that's 2, 4 followed by 19 zeros. And the period is 60 times 60 times 24 times 365. So that's the number of seconds in a year. Let's get down to this calculation here. Now, they say that the Earth takes 250 million years to complete its journey around the galaxy. So that means that the period is 7.9 times 10 to the 25 seconds. So I'm just going with some figures I found on some science websites. 250 million years. If I'm wrong about that, someone could correct me. I could adjust these figures if I'm out by any amount here. So the radius is 2.4 times 10 to 20. The period is 7.9 times 10 to 25 seconds. So that's a 7, a 9, followed by 24 zeros. Okay, we're getting into really big numbers here. So the acceleration is 2 pi over 7.9 times 10 to the 25. Did I get that right? Sorry, let me check that. 60 times 60 times 24 times 365 times 250, 123, 123. No, sorry, no, it's not. It's 15. Sorry, it's not 25. It's 15. Right, 15. Squared times the radius, 2.4 times 10 to 20, which gives you 2 pi divided by 7.9 exp 15 squared times 2.4 exp 20. It gives you, it's 1.5 times 10 to the minus 10. Now, okay, let me write that out for you so you can get this in perspective, right? This is what we're talking about. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 5 meters per second. Okay? That's the acceleration you experience due to the solar system rotating the galaxy. Now, they say that the galaxy is moving, sorry, the solar system is moving with a velocity of 483,000 miles per hour. That's what they say. Again, so that's a 0 there. 483,000 miles per hour. And again, just an arbitrary number. It's telling you how fast the solar system is moving relative to the centre of the galaxy. Doesn't actually mean anything because, again, velocity is relative. If you're not accelerating, you can claim to be stationary. So if you were moving with that speed relative to the centre of the galaxy and you weren't accelerating, it wouldn't mean anything at all for you. It would have no physical significance. What matters is the acceleration, and it's absolutely, well, to call it negligible would be to overstate it. Now, just quickly, I'll tell you what the roundabout result is for that. So if you're in a roundabout and it's got a radius of 3 meters and you're moving round, if it turned once every 10 days, you would feel an acceleration of 1.5 roughly times 10 to the minus 10. So that gives you some kind of indication of the sort of forces involved in our rotation around the galaxy, the effect it has on you. So I hope this puts this utter nonsense in perspective for you. The main one here is the one about the Earth. Where is it? Ah, yeah, here it is. Okay, just remember this one here, because they always bring up this thing about the Earth rotating at 1,000 miles per hour. It's not rotating at 1,000 miles per hour. It's rotating at 15 degrees per hour. And it's accelerating towards the centre of the Earth. Sorry, I'm on the wrong one. What am I talking about? I've lost the track of what I was doing now. Just a minute. Sorry, yeah. No, this one, yeah. Right, blethering. So, this is the one for the Earth. If you're on the equator, you're moving around the equator, you're moving at 1,000 miles per hour. It doesn't mean anything. You're accelerating towards the centre of the Earth at 0.03 meters per second, 1/327th of the acceleration due to gravity. The same force or acceleration you'd experience if you were on a disk with a radius of 3 meters rotating at once a minute. Okay?